Hey everyone, welcome back. I am absolutely thrilled to have you here for another explainer today. We are going to be exploring a truly fascinating intersection where standard digital electronics just crash right headfirst into physical biology and chemistry. We're talking about Fed pH sensors. It's an incredible piece of technology that essentially allows a solid silicon microchip to literally taste the acidity of a liquid. It's almost as if we've engineered a tiny, microscopic mechanical tongue.
Okay, let's dive into our roadmap. First, we'll go from MOSFET to Fed sensor. Then, we'll look at the anatomy of the sensor, the surface chemistry secret, translating pH to potential, taking the measurement, and finally enter the LAPS device.
I want you to keep this framing question in mind as we go through today's explainer. How exactly can a rigid, solid-state microchip measure the pH, the chemical acidity or alkalinity, of a wet, messy liquid? Bridging standard electronics with chemical reactions sounds kind of like magic, right? But as you'll see, it really just comes down to brilliant systematic engineering. All right, Section 1, from MOSFET to Fed sensor. Transforming a standard workhorse microchip component into a highly sensitive chemical sensor actually requires three crucial modification steps. It's kind of like following a recipe. First, we literally rip the roof off. We completely remove the standard metal gate from the top of the MOSFET. Second, we replace it by adding an H+ sensitive insulator. So materials like silicon nitride, aluminum oxide, or tantalum pentoxide are generally used here. And finally, step 3, we introduce a reference electrode directly into the liquid solution that we actually want to test. Moving right along to Section 2, Anatomy of the Sensor. When we look at the internal structure of the field effect device, or FED, we see the familiar P-type semiconductor with the N-type source and drain regions. But the top part is where the magic happens. The H+ sensitive insulator is in direct contact with the solution, and the reference electrode sits in the liquid, applying our gate voltage. I actually really love using a toll booth analogy for this. Think of the gate voltage applied by that electrode as the toll price. The drain current flowing between the source and drain, that's the traffic. Now, instead of a human changing the toll price, the liquid's pH actively changes the toll price right at that insulator surface. And that, in turn, controls the flow of our electrical traffic. Which brings us to Section 3, the surface chemistry secret. Now, if we zoom way, way in to the exact boundary line, the oxide and solution interface, we find the chemical barrier where surface groups interact directly with the liquid solution. Here, the OH groups on the oxide surface are actually interfacing directly with the ions floating around in the fluid right above them. And those OH groups actually have a name. They're known as amphoteric sites. At the oxide surface, silanol groups, which are written as SiOH, just naturally form. Because they are amphoteric, they act a whole lot like a microscopic sponge. Depending entirely on the pH of the liquid they are touching, these sites can dynamically either gain a proton or lose a proton. So the absolutely crucial point here is how this chemical reaction systematically turns into an electrical one. Let's simplify the surface chemistry for a second. Depending on the liquid, the sites protonate, meaning they gain H+ ions, or they deprotonate, losing them. The result of that? A net surface charge develops right there on the insulator. This newly charged surface acts just like a magnet, pulling in counterions from the solution to form a double layer. And it is this very specific double layer that gives rise to a measurable surface potential. Just like that, the chemistry has successfully created an electrical voltage. Okay, Section 4, translating pH to potential. Now, in electrochemistry, the absolute gold standard for how effectively a device translates chemical acidity into electrical voltage is called the ideal Nernstian slope. That number is exactly 59 millivolts per pH unit. What that means is, for every single step up or down on the pH scale, our surface potential should ideally change by exactly 59 millivolts. But whether or not we actually hit that perfect 59 millivolt ideal really depends on something called buffer capacity. Think of this as the density of active-reactive sites per unit area on our sensor surface. This is exactly why choosing the right H+ sensitive insulator is so critical. Materials like silicon nitride, aluminum oxide, or tantalum pentoxide are considered strong buffers simply because they have a massive density of reactive sites. A stronger buffer yields a much stronger, clearer electrical signal that closely approaches that ideal Nernstian slope. Weak buffers, with fewer reactive sites, they just give a much poorer, less reliable signal.
All right, let's jump to Section 5, taking the measurement.
When we graph the drain current against the gate voltage, something really interesting happens.
If you look at the curves for different pH levels, you'll see that as the surface potential changes with the pH, it literally shifts the FET threshold voltage. Changing the pH physically shifts the entire operating curve of the device linearly to the left or to the right.
To actually read this shift accurately, engineers use a really clever setup called a potentiometric feedback loop. Going back to our toll booth analogy for a second, we basically want to keep the traffic constant by dynamically monitoring the shifting toll price. First, we fix the drain current in the subthreshold regime using feedback electronics. Second, we measure the gate voltage applied by the reference electrode that is required to maintain that exact current. Because the electronics automatically adjust the gate voltage to perfectly compensate for the changing surface potential, that gate voltage shift gives us our precise pH measurement. Pretty brilliant, right?
And finally, Section 6, enter the LAPS device. Let's look at an evolutionary twist on this technology. The Light Addressable Potentiometric Sensor, or LAPS. When we look at the bottom half of a LAPS device compared to the FET model we saw earlier, you'll notice something huge is missing. There are no discrete source and drain regions, none at all. Instead, at the bottom we have pulsed light coming in, which generates electron hole pairs inside a depletion zone in the P-silicon.
Let's put the physical mechanics of these two devices side by side. The standard FET modulates a continuous electrical current through a standard solid semiconductor channel between a source and a drain. The LAPS, on the other hand, is an EIS structure, electrolyte, insulator, semiconductor. A bias voltage is applied, creating a depletion zone. Then, instead of standard current flow, pulsed light generates alternating photocurrents to measure the exact same surface potential changes happening at the ion-sensitive layer up above. And here's the real kicker. By simply moving the light source, you can measure the pH at different specific locations on a single continuous chip.
Which leaves us with a pretty incredible thought to ponder. If we can map the acidity of a microscopic fluid simply by shining a pulsed light on a piece of treated silicon, what other chemical mysteries could these hybrid light and silicon sensors unlock in biomedicine? I mean, from monitoring living cells in real time to creating high-density chemical imaging chips, the applications are practically boundless. Thank you so much for joining me on this explainer. Keep focusing and keep learning.